तो बस फॉरवर्ड कर दीजिए, अगर और एरी से कुछ ग्रुप्स वगैरह हैं उसमें तो।
एरी से ग्रुप में कर दिया होस्ट
मेरे को क्या कहते हैं, आपने जो मैसेज भेजा मुझे भी भेजिए, मैं फिर व्हाट्सएप पे डाल देता हूँ।
नहीं, वही सिर्फ जूम लिंक मैंने फॉरवर्ड किया और कुछ नहीं।
यूट्यूब वाला नोटिफिकेशन तो आ गया। वाली गाड़ी शायद थोड़ी खाली रहेगी। तो वो आने की वाली की गाड़ी में रिटर्न नहीं, बस से ही नहीं, ये कंबाइंड ग्रुप है दोनों का भाई
लाइव। तो जिस ऑर्डर में ये नाम है उसी ऑर्डर में स्टार्ट करते हैं।
आप लाइव है यूट्यूब पे?
ओके फाइन। कैमरा ऑन कर दीजिए। Okay, good morning everyone. Sorry for the technical delay. So International Women's Day, it's a globally celebrated day, celebrated on March 8 every year to commemorate the cultural, political and socio-economic achievements of women, with a wider aim of bringing attention to the issues that women have faced historically, such as gender equality, reproductive rights, violence, abuse against women. The day has its origin in various women's rights movements in multiple countries, and eventually it was formally adopted by United Nations in 1977. Since then, it's also a global holiday in many countries. Many countries celebrate it with various activities. And to paraphrase from International Women's Day website, a gender equal world is a just world free of bias, stereotypes, and discrimination against women. A society where diversity, equity, and inclusivity is not neglected. A world where differences are valued and celebrated. Only with collective effort, gender equality can be forged. Collectively, we can break the bias. Break the bias is also the theme for this year. So you'll also see this hashtag in social media posts and everywhere else. So starting our activities to celebrate this day, so we are going to have multiple such events at Aries. So starting today, we are going to have short talks by some of our women faculty, research scholars, and postdoctoral fellows. And so with this, I would like to invite Dr. Snehlata for giving the first talk. After each talk, we may have short question answer sessions if anyone has any questions. Otherwise, we'll move on to the next talk. So Dr. Snehlata, she will be talking on identification of variable stars in a young open cluster. Okay.
Good morning, everyone.
You can come here.
Today I'm going, topic of my talk is identification of variable star in young open cluster.
Okay, I'll do it from here.
Okay, so today's outline of my talk is, first I will talk about the introduction, then I will be talking about how I have taken observation, then finally I will be discussing results. So now I would like to tell what is variable star. A star is said to be variable if its brightness changes with the time. It could be two types, intrinsic and extrinsic. In case of intrinsic variability, luminosity changes with time due to pulsation or eruption. But in case of extrinsic variability happens due to eclipse or due to effects of stellar rotation. Next. Now coming to the star cluster. Star cluster is nothing but it is a group of stars which are found from same molecular cloud and roughly at same distance. And these objects are found from same molecular cloud. And these are classified, these objects are classified into two categories, globular cluster and open cluster. Basically in two categories. Globular cluster contains millions of stars, and these objects are found in the galactic halo. Till known 150 globular clusters are known. And these objects also contain RR Lyra type variables. Open cluster contains thousands of stars, and these objects are found in the galactic disk. There is another group called OB association. This group contains very massive and hot objects where star formation is still being taken place. Next. Now, because my work is basically based on pre-main sequence variability, so I would like to talk about pre-main sequence object here. So these pre-main sequence objects are still contracting and moving towards the main sequence. And in the HR diagram, these objects are found to be lying just above the main sequence. And their pre-main sequence states last about a few million years. And these objects are found to be lying inside the dust and gas. Pre-main sequence objects, these objects are divided into two categories, T Tauris and Herbig B stars. T Tauris are very young solar type stars, and their mass ranges from 0.5 to 2 solar mass. And they show strong hydrogen and lithium lines in their spectra. And Herbig AB stars are normal AB type stars, but they show emission lines in their spectra. Next. Now T Tauris are further divided into classical T Tauris and weak line T Tauris based on spectral energy distribution and strength of H alpha emission line. T Tauris have large NIR axis and show strong emission in H alpha wavelength, while weak line T Tauri have little or negligible NIR axis, as you can see from this diagram, where these class 3 object is having almost negligible circumstellar disk around it. Next. Now coming to the causes of variability in pre-main sequence. In pre-main sequence star, it is thought that variability occurs due to presence of cool or hot spot on their surfaces. And in case of weak line T Tauris, variability happens due to presence of cool spot on their surface, while in case of classical T Tauris, variability occurs due to presence of hot spot. And these classical T Tauris show irregular type of brightness variation. We can please next. Now, high study of variable stars is important. The study of variable star is important because with the help of variable star, we can get to know the physical parameter of stars, and we can also learn about the internal chemical composition and stellar structure and physical processes which are responsible for this stellar structure. And we can also learn certain stellar environment if we are studying pre-main sequence variability. Why variability in open cluster? Because we do variability in open cluster because these objects, we can use basic properties of open cluster to characterize the variable star easily. And we can also understand evolution of angular momentum if we are doing pre-main sequence variability. Next, please. Now, so with the aim to derive the rotation period of pre-main sequence objects, we have selected one open cluster NGC6823. It is a very young open cluster which is lying in bright S2 region, sharpness 86, at a distance of about 2 kiloparsec. The ranking toward this cluster is found to be varying from 0.7 to 1.1 magnitude. In 2016, Riaz et al. Did photometric observation and found a large population of class 1, class 2, and class 3 objects. And in 2000, Pigulsi et al. Did photometric observation of this cluster and detected 15 variable stars around the cluster. Out of 15, 2 stars were identified as a delta Scuti variable of pre-main sequence nature. So we have observed this cluster, and this is 6823 from 0.81 Tenagra automated telescope located in southern Arizona on 54 nights. And we have secured 232 frames in V bands and 243 frames in I band. For doing the pre-processing of the CCD frames, we have used IRAF, and for photometry, we have used Geophot software. This figure is showing the image of cluster NGC6823. Next, please. Now, coming to the identification of variable star. We have identified variable stars in this cluster by seeing their light curve. And to confirm their variability, we have also used RMS dispersion techniques. So in total, in the region of this cluster, we have identified 88 variable stars. Here, this is the figure between RMS and instrumental magnitude in I band, where circles are representing identified variable star in the cluster. Next. This figure shows the light curves of some of variable stars identified in the cluster. Here, this figure left one is the real-time light curves of some variable star, while this left figure shows the phase light curve. Here I want to tell that for me, it was not easy to detect those variable stars because we do not have internet observation for this cluster. So it was very difficult for me to identify variable star in this cluster. Now coming to the membership. In order to assign the membership to the identified variable stars, we have used these following diagram, like V versus V minus I, color magnitude diagram, J minus H versus H minus K, color magnitude, and some other more color diagram. Here in the first one, color magnitude diagram, here this solid line is showing theoretical model given by Girardi et al. 2002, and horizontal lines are pre-main sequence evolutionary tracks for different masses. And this diagram has also been used to determine the masses and ages of pre-main sequence objects. So in using these diagrams, we have identified 72 variable as a probable member of the cluster, and this is 6823. Next. Now, among 72 probable members, 42 are detected as a pre-main sequence variable, and these pre-main sequence variable could be T Tauri stars. And out of 48, 8 are classical T Tauris and 40s are weak line T Tauris. And the remaining 24 variable could be main sequence variable, and these main sequence could be beta sub, delta scuti, and slowly pulsating. Here, this diagram between luminosity and temperature, and this has been obtained by using some relations. This is basically HR diagram where identified main sequence variables are located. Next. Now coming to this summary. We have done photometric monitoring of NGC 6823 using 0.8 meter Tanagra automated telescope in southern Arizona on 54 nights from early October to December 2012. And in this cluster, we have identified 88 variables. Among 88, 72 could be probable member of the cluster, and the membership has been established on the basis of UVVI and IR data. Among 72, 24 could be main sequence and 48 are pre-main sequence members. Thank you. Next.
Okay, any questions? People attending online, if you have any questions, you can raise your hands or type in the chat box. Meanwhile, maybe I can ask one question. It's a very general question. So this open star cluster usually have, the stars usually have similar age, right?
Yeah.
As opposed to globular clusters.
Yeah, roughly they
Yeah,
have
roughly same age. So the periodicities that you see in the variability,
yeah,
are they of the similar order in the stars?
Periodicity means period. Period is different from the age.
No, I'm asking about the variability period that is there in members of open star clusters.
It changes with the age. Means even some stars means are like a classical T Tauris and weak line T Tauris. So with age means it should be faster.
Okay.
So means the rotation period of these weak line T Tauris should be faster. Means faster. They should rotate faster. So, but still we are doing this. So.
Okay. Thank you. Others, any question?
Yeah, I have a question. Can you hear me?
Yes, sir. Please go ahead.
Virendra, yeah. In the same line of thought, of course, there is a famous Skumanich law, which is related to the, of course, the age and the rotation and all that. So, is there, those things can be tested in some of these clusters? As Virendra was mentioning, of course, in open cluster, the ages are more or less same. But from the star cluster studies, are the Skumanich law very well verified?
No, sir, I have tried to see the relation between rotation period and this age, but sometimes I did not get any relation between these two things.
But the Skumanich law, I guess you are aware, no? This has also something to do with the.
Yeah. In my some paper, I have done this thing.
Okay. Yeah, because that's very interesting in the context of the sun as well, because the rotation period
Yes,
and
sir,
the
yes.
magnetic field,
Sir.
how the magnetic field changes, the stellar winds, all those things are pretty well related.
Yes,
So
sir,
in
yes,
the,
sir.
in the context of stellar cycles, people do that kind of thing. So how does star cluster studies help in that process? I was just
Yeah,
wondering.
yes, sir. But we do not have a large sample. So if we will have a large sample, then we will try to find this relation very well.
Okay. Okay. Thank you.
Anyone else? Okay, if not, we'll move on to the next talk. Thank you, Dr. Snelata.
Thank you.
The next talk is by Dr. Neelam. And let me just start the presentation. Yes.
Thank you. Good morning, all. So here I will be presenting the star formation in young clusters and H2 regions. So,
I can change it. I can change it.
okay, so when we talk about the star cluster and star H2 region, so basically most of the stars, they are forming in the star forming region and out of molecular clouds. So the dominant mode of star formation is the cluster, and hence young clusters are the sites of stars which have like a wide range of mass, and they are also at the different evolutionary stages. So they are like young clusters and H2 regions, they are the best sites to study the pre-main sequence evolution of the young stars, as all the stars are at different evolutionary stages, but have nearly the same age. And we can also study the environmental effect on the star formation when we study the star formation in young clusters. Okay, so as I told that stars form in a variety of masses. There may be a very massive stars, and massive stars have generally mass greater than 8 solar mass, and there are like some stars which are like sun type stars or low mass stars, so they have masses which are less than 2 solar mass, and there are intermediate mass stars also between 2 to 8 solar mass. So there are like red dwarfs which have masses like less than 0.4 or 0.5 solar mass, and we know that there are like stars which the stars can have masses up to only 0.08 solar mass, and below this there are brown dwarfs and also gas giants. So in the first part, I will discuss about the radiative feedback effect of the massive stars, because massive stars are have masses greater than 8 solar mass, and they also emit strong ultraviolet radiation. So as the massive star turns on, it begins to ionize its surrounding molecular hydrogen and creates the bright H2 regions, for which the temperature is of the order of 10 to the power 4 Kelvin. And when this H2 region expands, there may be they may have a different kind of feedback on the surrounding molecular hydrogen or surrounding parental molecular cloud. So in a first feedback, which is positive feedback, the H2 region can just apply the correct or apply a push on the molecular cloud and induce it to the collapse and form new stars, or it can trigger the star formation. And in a negative feedback, massive star may disrupt and disperse the molecular cloud, and thus it can inhibit further star formation. So this is a kind of negative feedback. So when we talk about the triggered star formation or induced star formation, so in case of induced star formation, we can see star, because most of the stars, they are forming in the cluster. So here in this figure, we can see a massive cluster, massive star, which is at the center of the cluster, NGC 3603. And we can also see a different kind of structure, like dense dark clouds and global type of structure in this this star forming region. So next slide. Okay. So expansion of the H2 region, it can trigger star formation at the periphery also. So this is just an example. It is a H2 region, RCW79, and here at the border of this H2 region, some molecular clumps are found, which are already showing that this may be a massive star at the boundary of the H2 region. Okay, and in a similar way, this is a giant H2 region cloud complex, which is known as W5. So here at the there are mainly two subregions. One is W5 East and other one is the W5 West. So these are excited by two different massive stars. So in the eastern part, we have this global-like structure. These are called the bright rim clouds, which have a bright rim which is facing towards the H2 towards the massive star. So we can see many such globules or irradiated structure in the H2 region. And
we press this and move.
Yeah, so this is one of the bright rim cloud. Here also, this one's bright rim cloud. So here you can see these are the bright rim clouds, and you can also see some small structures here. So so the main cluster is somewhere here, and this is the massive star of the cluster. Here also we have the massive star here and cluster also. So sometimes in these type of star forming regions or H2 regions, we can also see age sequence. So in this, when we estimate the ages of the young stars in these H2 regions, so we found that most of the stars which are younger, they are inside the cloud, and most of the stars which are outside the cloud, they are arranged in a way from ionizing star to the this bright rim cloud side. So, and these are the other structures which are called the elephant trunk-like structures in the H2 region.
So these kind of elephant trunk-like structure, these are very common in many of the nebulae where star formation is going on. I've seen. So what is the origin?
Yeah, so there are like different origin mechanism for these. So some of them are like when we talk about the triggered star formation in H2 region, so some are like collect and collapse model. One is radiation driven implosion. And this kind of structure, these are basically due to the hydrodynamical instability.
Okay.
So
next.
So in one of this region, W5 East region, we already found the age sequence, which was from this is the HD 18326. It was the ionizing star or massive star of the cluster. So we found the age sequence in where the stars which are towards this BRC14 side, they were younger as compared to the stars which were towards this ionizing star side. So this is called a small scale sequential star formation. So we can see that the star which is at the center, this is the first generation star, and the stars which are forming inside the this remnant cloud, these are the second generation star. Yeah, so these are these elephant trunk-like structures. So we have found this type of structure in other H2 regions also. And when we carefully see these elephant trunk-like structure, we found that there are 1 or 2 stars in many of these elephant trunk-like structures tip. And these are basically the young sources, class 1 or class 2 sources. And this is for another H2 region, which is W4 H2 region. So these, what we did, we identified the young star in this H2 region, and when we plotted, so we also traced the clusters and distributed mode of star formation in this H2 region. So we found around 5 cluster in this H2 region, and there are like some dispersed young stars in the H2 region. So this is the main cluster, and here we have many massive stars in this H2 region around this young cluster. So we also found this kind of elephant trunk-like structures in this H2 region also. And again, when we we found the age and their classification. So these were mostly class 1, class 2 sources, and these were very young. So from this, we say that some of the young stars, which are like distributed young star inside the H2 region, so they may be formed in this type of elephant trunk-like structure. So their origin is basically due to triggered nature of the star formation. So, and this is another H2 region, which is SH2112. So in this H2 region, where the massive star is this one, and at the periphery, we found some active star forming sites here also. And yeah, so from it, we can see that we did radio continuum observation for this H2 region, and we found 2 peaks. One is here. This is the ultra compact region we have identified, and also we have identified this type of structure, which is known as the ionized boundary layer. So basically, this is between the, and here you can see very clearly, this is the ionized boundary layer, and this is the compact H2 region. It also consists of a star, a very young star, and we could calculate that this is a massive star. And so when when we calculated the flux of this ionized boundary layer here, and we also calculated the pressure. So pressure inside the molecular cloud was less as compared to the pressure of the ionized boundary layer. So from that, we argued that the star formation, whatever is occurring in this cloud, this may be due to the triggered star formation. And the next, we can also do initial mass function study with the young clusters. So like here, this is a sigma Orion cluster, and it says it's around 3 million years. So EV minus V is very less, around 0.25 magnitude, and distance is also very less. So in this cluster, there are many studies, and they have found objects which are like very low mass objects, below 70 Jupiter mass or below the brown dwarf limit. Also they have studied in this cluster. So we can use these young stellar clusters. If we have a deep photometric or spectroscopic observation, we can study the stellar and substellar mass object in the very young clusters. So the ratio of stellar and substellar mass objects, this can also be used to as a proxy to compare the shape of the initial mass function in very young clusters. So here I'm showing this is a very young cluster, Berkeley 59, and it also consists of very massive stars. So the deep optical and near infrared photometry of these two subregions we did, and when we plotted the HR diagram for this, so we could detect objects up to 0.2 solar mass, and we also we found that the initial mass function slope of this for this cluster is similar to other open clusters, young clusters, and this is another result, which is based on the near infrared JHK, deep JHK observation of the same region using the same telescope. And here we have identified the young stellar objects in this region, and we have plotted this. This is the isochron for 2 million years for the same age of the cluster. And so from here, we can see that we are able to trace the objects up to 0.03 solar mass, which is well below the brown dwarf limit. So we are still working on this object, and so we have also found that stellar to substellar mass of objects ratio is around 4 for this region. So if we if we know the stellar to substellar mass objects or IMF at very low mass, so we can also study the origin of these very low mass object or substellar mass objects in the clusters. So this is the main aim of this study. And here I will summarize the main results, that young clusters and H2 regions, they contain stars of a wide range of mass. So they can be used to study the star formation scenarios and star formation processes in the young cluster. And also we can also study the environmental effect of the massive stars on the nearby molecular clouds and further star formation activity. And this also can be used to study the evolution of the pre-main sequence objects or pre-main sequence stars. And this photometric and spectroscopic observation with a large telescope, they can also be used to reveal free-floating planetary mass objects or objects which have masses well below than the brown dwarf limits. Thank you.
Any questions? People online? Okay, if not, then we'll move on to the next talk. Thank you, Neelamji. The next talk is by Dr. Anjali Kathekal.
Hi, I hope you can hear me well.
Yeah, we can see the slides.
All right. So shall I stop the video? I think it's better with the
network. Sure.
Yeah. All right. Very good morning, everyone. First of all, happy Women's Day wishes to all of you. I am Anjali. A few months back, I joined as a postdoctoral fellow in the Solar Group. So I will be giving a very general, brief outline of what I am working on, not exactly what I'm working on, but where my interests lie. So it's about decoding the sunlight. When we think about a star, which is our host star, it's the light and heat that emanates from the sun that sustain life on our planet Earth. And for me personally, what interests me the most is what hides behind this white streak of light that we receive here on Earth. And most of you might be aware of this image that I have shown here. It's the famous dispersion experiment conducted by Sir Isaac Newton in the beginning of 18th century. So this is a very simple setup. We currently now call it as a basic spectrometer setup. What he did is that he focused the sunlight through a narrow slit onto a prism. And what he found is that white light, or what we call as visible or the optical light, it's split up into constituent colors easily, and you get a very familiar result that you will end up with a rainbow. So what actually hides behind this white streak? And it all starts with the simple experiment by Newton, and a very detailed analysis of solar spectrum came almost a century later. And this was done by a German physicist called Joseph von Fraunhofer. So before going into all those details, we all know that spectra basically is nothing but the description of intensity or light as a function of wavelength. And if we consider star, it's a G2V star, where G2 stands for the spectral class, which is based on the color. The previous speaker gave some explanation of different stellar classifications, and 2 stands, it represents that sun is the second hottest star, and then V stands for, it represents that sun as a main sequence or a dwarf star. And the second classification that it's based on spectral type, which is temperature based. And since I talked about these 2 classifications, you must be familiar with how different kinds of stars are classified based on their color and temperature. Since we are celebrating Women's Day today, I thought it's the right time to mention about 2 of these brilliant scientists for women. The first one is Annie Cannon. She was the one who actually classified stars based on their colors. And it was about 3 decades later, another woman scientist called Cecilia Payne-Gaposchkin, who classified stars based on their temperatures. So now we are using this classification based on temperatures, and we know that sun belongs to the G2 class, which means that it's the second hottest, and it has a surface temperature of about 5,800 Kelvin. So what is the importance of knowing the temperature of stars, or sun, or any star for that matter? The thing is that if you know the temperature of the stars, it can give you an understanding of how they are born, how they live, and ultimately perish. Now, coming back to what I was telling before, the Fraunhofer spectrum, it was this German physicist who gave a detailed description of how sunlight spectrum is expanded into. And what he found is that if you look at the sunlight and divide it, split it based on wavelength, he noticed that there are very specific positions where you don't see any presence of light. And these are called absorption lines, or the spectral lines in our terminology. And if you look at this particular spectrum, you can see very clear signatures of strong absorption lines, which are where the lights are not visible. So if you look at the first one of these are the famous calcium 2 K and H lines. And then you have the H delta, H gamma, H beta lines, and finally the H alpha line. Sorry about that. So these H lines, they are all coming from the Balmer lines, which are in the visible range. And then you also have this famous sodium 1 doublet line. So these are all lines in the visible spectrum. And so when you look at when you look at all these spectral lines or the absorption lines, what you can see is that they come from very specific elements, and it means that the sun has an atmosphere and you have these absorption lines formed due to very specific transitions that result from these elements that are present in the atmosphere of the sun. So when you want to study a spectral line or any light that is emitted from any source, it involves a number of processes. Basically, it can be split into two. One is the atmospheric process, which involves the propagation of light through any atmosphere, in this case, the solar atmosphere, which is actually a large-scale process. So it is macroscopic in nature. And then you will have to deal with the atomic processes, because all these very specific locations where you get the atomic the spectral lines, they correspond due to very specific line transitions, whether it is from the atoms or from the molecules. So you need to know about the absorption or emission that is involved with bond-bond transitions. And these are microscopic in nature. So basically, the formation of a spectral line involves a large scale and a small scale processes. Now, when you talk about spectral lines, what we use is spectroscopy, the technique which helps us to map the atmosphere of the source that we are concerned with. And it helps us to do this in a 3D model, yes. So for example, if you look at this, on the left is a spectral line, which is the H-alpha 656 that I showed in the Fraunhofer map before. So basically on your left side, x-axis is your wavelength shift and y-axis is your normalized intensity. So as you pass through each of these wavelength points, you see on the right that you get very distinct features shown up on the image. So when you come very close to the core, you get a very diffused kind of features. And when you move away from the core of the spectral line, you see that very famous convective nature of the solar surface, which is represented by granules and intergranules. So what actually a spectral line does is it gives you information of the multiple, the different layers of the solar atmosphere. You get temperature information, you get velocity information, you get the formation depth of this particular spectral line. So spectroscopy actually helps you understand various physical properties of the atmosphere that you're looking at, all sorts of physical parameters. And if you're taking specific features on the sun, we can resolve the solar surface in such a detail because it's very close to us and it can do the purpose of being a plasma laboratory, which we can use to study what is happening on the other stars as well. And here I have shown data taken from one of the space telescopes called Hinode. It provides very high resolution data. So what is shown here is an intensity map. And some of you might be familiar with what's shown here. It's called a sunspot, which has a very distinct structure called umbra. That is the darkest region. And then you have another structure surrounding it called the penumbra, which is brighter compared to the umbra. And if you're looking at a spectroscopic data corresponding to this particular image and choose maybe 2 points, for example, one inside umbra and one outside of this umbra and penumbral region, say B, for example, what spectroscopy can give you is how distinctly different the spectrum corresponding to these two very different regions of interest or very different points of interest. So you can, if you look at this particular image, so this is again wavelength shift, and the position along the y direction. So it's basically the intensity information shown here. So you can see that corresponding to the point A, your spectral line is split into 3 components. But if you look at the point B, you don't see anything particularly visible in the spectrum of this region. So, and this is a representation of how you look at things when you're looking at the region through a slit spectrograph. And if you look at actually the spectrum, this is how it would be. And you have a very distinct splitting that is seen in the emperor of the sunspot. And when you look at the other region that is B, you don't see anything significantly dominant as that is seen at the point A. Now, this is not the only thing. If you have access to different filters, what you can do is simultaneously map different atmospheric layers at the same time and get information from different layers, whether it is spectroscopic or if possible polarimetric as well. So here is an example of that. You can actually do a multi-layer scanning using, so this is taken from a space telescope. Again, it's called Solar Dynamic Observatory. And on the left side is a continuum or the white light image. And then you have another filter that is representing the upper atmospheric layer called the chromosphere. And on the rightmost side, you have the corona, and it's taken at a different filter. So what you can see is that these are all representing the same region and its entire disk of the sun, but you clearly see there is a distinct difference between, there are distinct differences between all the 3 filters. You see certain specific features in only some of the filters. For example, you don't see these kind of loop-like structures in either of these images, and these are the structures where plasma is moving along the magnetic field lines. And this is in the visible, and these 2 are in the EUV range. So when you use spectral lines or spectroscopy, they help us to interpret various kinds of dynamic processes that we observe across different layers of the sun. So this is the advantage of having a multi-layer scanning or a 3D information of the source you're looking at. So we have been talking all about intensity information, but that's not the only thing that you can do with a source like sun, which is very close to us. So another thing is that you get polarimetric information, which give you access to understand what is happening magnetically in the source region that you're looking at. For example, this is the same image of the, it's not the same image, but it's taken of the same region, but it's a polarimetric information. So if you look at the points A and B, you can actually get different parameters like Q, U, and V, which represents the magnetic field parameters of the region that you're looking at. So basically you can get physical parameters like temperature, velocity, and depth of formation from your intensity information that's given by Stokes I, and then you get how the magnetic field is evolving or it is oriented, how strong it is, those kind of information from the polarimetric data. So combining all these and looking at them at very small spatial scales and inverting them using specific inversion codes is what I am doing at the moment. So that's my personal interest, and that's what I do. Thank you for your attention.
Thank you, Anjali.
Yeah.
Do we have any questions? If not, let us move to the next speaker. And Next talk is by Dr. Priyanka Jalan. And she'll be talking on what's between us and quasars. So let me just start the presentation. This one. Okay.
Yeah. Okay. Hello, everyone. My name is Priyanka Jalan. I'm currently a post-thesis fellow at Variability Research Institute of Observational Sciences. And today I'm going to talk about the material which is present between us and quasars, which is known as the intergalactic medium. But before I go into the detail of it and what I do regarding this, so I'll talk about the quasar spectrum and what is actually intergalactic medium. So firstly, thanks, Dr. Anjali, because you have given a wonderful talk on spectrum. And so that's why I don't have to explain what is actually a spectrum. Now, similar to what Anjali has already explained, that a star has a spectrum. Similarly, for a quasar also, it has a footprint which can be explained by its spectrum. Now, if there is any material which is present between us and the quasar, the evidences of that particular object will also be imprinted on.
Sorry to disturb, Virender, screen is not shared. Could you please share the screen?
Oh, okay. Yeah, sorry about that. I hope it's visible now.
Is it visible now?
Vaidehi, can you see the screen?
Yes, I can see the title slide.
Okay.
Okay, great. Right. So yeah, I was just mentioning about this, that if there is a quasar and it has a spectrum, and if there is a galaxy in between, we will see the evidence of this galaxy, even though it is not directly observable from Earth, but we will see the evidence of this galaxy as an absorption in the spectrum of a background quasar. So we know the existence of a galaxy based on the absorption lines seen in the spectrum of a background quasar. So similarly, all the material which is present between us and the quasar will also be imprinted on the quasar spectrum. But at first, how do we know that there is any material which is present? So how do we know firstly that there is a material which is present between us and the quasar? So it comes from the structure formation theory. We saw the spectrum of the quasars and we see that there are some absorption lines. I'll come to that in the next slide. So from the structure formation theory, we know that there are these primordial fluctuations and dark matter potential well, in which the baryon starts to fall and form these galaxies and clusters and superclusters. So you can see from this image, where I have shown one example, that there are some plants which I'm taken from the Aries garden, and these flowers are actually representing the clusters, or you can say the galaxies, and when they are in very vicinity of each other, they cause this super clusters or galaxy clusters. But in overall, we see a distribution of this green material, which is known as the intergalactic medium. Why this happened is that when this structure starts to form, most of the baryons actually fall into these dark matter potential, but some of the baryons actually remain in between these galaxies or these galaxy clusters, which is known as the intergalactic medium. The names comes from this fact only because it's a medium which is present in between the galaxies, and that's why it's intergalactic. So the intergalactic medium was initially neutral, which is mainly comprised of neutral hydrogen. But as these structures starts to radiate, they ionize the intergalactic medium, and we get an epoch of reionization where this intergalactic medium is almost ionized. And what we see today is an ionized intergalactic medium. Now, what we can do is that we can use this as a background quasar, and we can study the imprints of this intergalactic medium on the quasar spectrum. So firstly, coming to the fact, what is quasar? Quasar is actually a subclass of active galactic nuclei. And if we see a cartoon figure here in the left side, we have a supermassive black hole in the center. It is surrounded by an accretion disk, which radiates a continuum, a power law continuum seen here. There are some clouds which are in the vicinity of a supermassive black hole. And because they are very nearby to the supermassive black hole, they lead to some broad emission lines. There are some clouds which are further away from these supermassive black hole, and therefore they leads to some narrow emission line. So there is also a dusty torus. And in the case where the quasar orientation is such a way that the torus is actually hiding these broad emission lines, we are only able to see some narrow emission lines and not the broad emission lines. So these two different classes are known as type 1 and type 2. So type 1 is where we are actually able to see both broad line region clouds and narrow line region clouds. And for type 2, we are only able to see the narrow emission lines. So we see a continuum as well as the emission lines in a quasar. This is a very low redshift quasars, and we are just seeing the continuum and emission lines. But if we place this source at a further distance, what we can see is that if there is a number of absorbers, so dependent on the density of the absorber and their position, we will also see the absorption in the quasar spectrum. So if this is the initial light, what we will see is the absorption dependent on the density and the position of the absorber, which is present between the source and the observer. But here I'm going to talk about the universe, which is not actually a static universe, and it's expanding at an accelerated rate. So what is happening is that any wavelength which is emitted from the quasar is redshifted as it travels to the observer. So if we are just talking about the Lyman alpha absorption here, so there will be many wavelengths which are at a lower wavelength, but they are redshifted to a Lyman alpha wavelength as it travels through the universe. So as it passes through the universe, all the absorbers which are present, it is absorbed by those absorbers, and dependent on their density and their size, we will see the absorption at that particular location. So this is what our typical quasar spectrum looks like. Sorry, there was a video here, but I'm not able to run that. But if you can see in the upper panels here, that if there is a Lyman alpha absorption, so this is the continuum here, which is coming from the quasar, which we also saw for the low redshift quasars. But as it passes through the intergalactic medium, we see these narrow absorption lines. And the corresponding Lyman beta and Lyman gamma are also seen in the spectrum. So now we understand that there are the imprint of the intergalactic medium is imprinted on the quasar spectrum. So I'll be talking about this particular region, which is the Lyman beta to Lyman alpha emission line, which I have zoomed in the lower panel. So this is the Lyman beta emission line, and you can see that there are various such multiple absorption lines, and it seems like they are just dips. But if you zoom in the little bit on these absorption lines, you see there is a structure. These absorption lines have a profile. And this profile can be well understood with a Vogue profile. I'll come to that in next slides. But why this particular region is of interest, this Lyman alpha forest? This region between Lyman beta and Lyman alpha is basically pristine neutral hydrogen absorption. If you see a cloud 2 here, it will also has a Lyman alpha absorption here, but also there will be an overlap of the Lyman beta absorption from this cloud 1. So beyond Lyman beta emission line, there will be a chaos of Lyman alpha and Lyman beta absorption. But here in this particular region of Lyman beta and Lyman alpha emission line, you will only have Lyman alpha absorption lines. And if you zoom in here, as I said, that there are various structures you can see. So these absorption lines are well defined with a profile known as the Vogue profile, which is a convolution of Gaussian and Lorentzian profiles. In the right panel, I'm showing one example here for different column densities. So these Vogue profile can be well defined with two parameters, which is basically the velocity width or the Gaussian part of it. And another is the column density, which identifies the optical depth of this absorption lines. So you can see as the column density is increasing here, you're able to see that the absorption or the optical depth of the absorption line is increasing. So why is it important to study the column density or the velocity width of these absorption lines? Because once we know the velocity width and the column density, we actually know the density and the temperature of the intergalactic medium. So we can actually calculate or map the B and N space to a temperature and density space, which will help us get the information about the intergalactic medium thermal history, and also it is evolution with the redshift. So once we know all these parameters for these absorption lines, we can actually calculate the thermal history. We can understand the ionizing background. We can understand how these lines are evolving with the redshift. But although all this seems very easy, but you can understand that fitting all these work profile manually will be very difficult task. And you can see in this previous particular case that you have so many Lyman alpha absorption lines. So if you start to doing it manually, it will take forever to do it for even just for one quasar at high redshifts. So instead of doing it manually, what we are doing is we are using machine learning, and what takes hours, even with the semi-automated codes for work profile fitting, it will just take seconds, and it will give you these B and column density values within seconds. So firstly, I'll tell what is machine learning. It is similar like how you teach a small child about new objects. So suppose there is a child and you teach him that, okay, this is a car. So what he understands is, he or she understands is that, okay, it has 4 cars, it has 4 tires, and it has a window, it has this doors. Okay, then this is a car. But maybe there is a small truck and it misidentifies it as a car. So what your mother will do is, or my father will do is, that they will say, okay, no, this is not a truck, this is not a car, this is actually a truck. So it stores a feedback. So what it's doing is that it takes input data, it analyzes the data and find patterns, the tires and windows and everything. And it makes a prediction. And whether it is correct or not, it is stored as a feedback. So next time it will see a truck, it will identify as a truck. So this is what machine learning does exactly. But firstly, we train with a lot of data, which are labeled data. So that means we have these training data set, which are labeled as circles, squares, and triangle. We make a model, we train the model that, okay, this is this and this is this. And next time when it gives an input data, it predicts whether it's a circle or not. So it predicts it's a circle. So dependent on how good your model is, it will identify it accurately. So it's not about, firstly, how well it is identifying a new object, and also for how many times. So now if you give a circle again, whether it again identifies it as circle or not. So this is how you identify how good your model is actually working. So I have a very good example here. It's a classification example, although in our case we will be talking about regression analysis, but it's a classification example. Like if you feed a machine that this is a koala image, and you have to say whether it's a koala image or not, you have to train your machine like that. What you will do is you will identify various parameters like koala's eyes, koala's nose, koala's ears. And if all of these 3 parameters are saying it is a yes, then only you will say that it is a koala head. So it will say yes in that case only. And if similarly for the body. But now you can obviously give a bias that if it's a koala's head, then it's probably a koala. So you can give a bias to koala's head, and it will identify it as a koala. So you do it with various such images of koala. You give as a training data sets, and you give these labels that, okay, this is koala, and you will just give random horse images or something like that, and say that, okay, this is not a koala image. So when the model is trained with this idea, and then you again give a koala image, it will identify it as a koala if your model is working well. So similarly, what we are doing here is that we train our model with various such work profiles. So we simulate these work profiles and we make them as real as possible. That is, we convolve it with the spectral resolution. We add signal to noise to these absorption lines, and we train this for a given B and N value. Once our machine is trained, it can actually identify whether the next value which we are giving is actually, it will predict the B and N value. So there is something called a validation data set for which you already know the labels, and we ask the machine to predict for us. And then we plot this to see how the model is working. So I'm not showing the model here because it's still unpublished. But once we have this model is well trained, then we give these B values and N values, and we ask the model to predict for us. And you can see here that our model is working pretty well. This red is the 45-degree line, and most of the points are actually lying within this red line. And these are actually 1 million points. So it's actually good. I mean, there are only few points which are lying outside this red dash line, red solid line. And this is actually showing the histogram of true value and predicted value. And you can see the spread is only spreading up to 2.5 kilometer per second, which is really good. I mean, it's doing very well. So here's another example. If you have the spectrum, you have this multiple absorption lines. You can see the model is predicting the B and N value for the given B and N value. So we know the true value and we know the predicted value. It's what it is not detecting is these absorption lines. But you can see these are not, that even you cannot detect these lines because they are hidden in the noise. So for the lines which are actually visible and they are like 1 sigma higher than the noise, lower than the noise actually. So then you can use these lines and the model can actually predict. So this blue line is what the data is, and the orange line is what our model is predicting. So it is fitting pretty well actually. But life is not so easy, and instead of single absorption lines, we actually have multiplets absorption lines, as you have seen in the previous slides also, that the structures are actually something like this, the solid part. So it's coverage. I mean, it's the both multiplets are combining and forming this kind of a structures. And here I'm limited to 6 such multiplets getting blended together. And this is what our model is predicting. So this green is what is the true absorption lines which we are seeing. And the purple is actually what our model predicts. So in the case where we have like higher multiplets getting blended together, our model is getting wider uncertainties. But for small or single absorption lines, at least for the low redshift quasar, our model can well predict these B and N parameters. So our goal is that once we have a very good model, which can even predict for higher multiplets, we can get these B and N values, and then we can go back and map this B and N to the temperature and density of the intergalactic medium. So I would request that if you want more information on machine learning, you can scan this QR code. And I will end with this joke that if you train your machine, you train it a lot and lot. And finally, it just says 8 number. You ask this to predict what is this number, and it will predict 8. So you are just tired, and maybe you will just move on to the next model. And this is how actually we get a lot of models you have to try, which works best for your training data set. I guess thank you here.
Thank you, Priyanka. Are there any questions?
Hi, Priyanka. It was a very nice talk, very interesting, using neural networks. So when you have this line blanketing, like when you have multiple line blends, would you be able to actually differentiate between how many lines are blended and how you can separate the temperature and density between those blends?
Yeah, actually, so can you just go this back? Yeah. So here in this case, you can see, basically the green solid is actually what is true. So what we are seeing is actually a blend of these 3 lines, which is the dashed green lines shown. So actually our model can predict number of blends which are happening. So this purple dot dashed is what our model is predicting. So I mean, it is predicting two of the absorption lines correctly, but for the one, it is actually shifting a little to the righter side of the velocity. So I mean, ultimately we want that it should exactly get the what is a true value. But yeah, I mean, our model can actually identify how many multiplets are actually getting blended in that particular absorption line.
All right. So do you get any significance levels or something to say that this?
Yeah, so what we are doing is that we are calculating a mean square error, what our predicted value and true value is between them. So for ours, so I think I'm showing here somewhere. Yeah, so in the top panel, you can see that we are writing the mean square error. Here, I mean, for column densities, it is working very well actually. But for the B parameter, our mean square error is still large. But I think this is happening because of this scatter at very high and very low velocities which you can see also from this plot.
Yeah, right.
Yeah. So, but yeah, we're calculating mean square error as well as the root mean square error from the true and predicted value.
Okay, great. And just one more question. So, is there any, if it is known, is there any acceptable value of your deviation from this? I mean, that you would give as a condition to your neural network model?
Right. So what we are doing is that we already have some data which are manually fitted by we have fitted them manually. So not I have done it, but like other people have done it. So they have fitted the work profile, and this is the best like what we have already. So what we are trying to do is that we will use that data and use our model to fit those data, and we will see from the human perspective and from the model perspective, which one is getting better. I mean, these are best fitted data, so our model should be as close as to that best fit data.
Yeah,
so, yeah,
that's fair enough. Yes.
Yeah. So we'll just calculate how good that is working, and I think that will decide how good our model is or not.
Oh, yeah. Yeah, that's fair. Yes. Thank you.
Thank you so much.
Any other question? Okay, if not, then let us move to the last talk of the day by Bharti Arora, Winds from Hot Stars.
PDF.
PDF. Okay.
Yeah. Pointer is not there.
No, for pointer you have to press this and then move it.
Okay, thank you. So good afternoon, everyone. So first of all, I want to thank the organizers for arranging this session on the International Women's Day occasion. So today I'm going to present a talk on the stellar winds. So title of my talk is Winds from Hot Stars. So by hot stars, I mean to say the massive stars which populate the upper left region of the HR diagram as shown in this picture. So these stars have mass typically larger than 8 to 10 solar masses, very luminous, having luminosity around more than 10 to the power 4 solar luminosity, and they are hot stars having temperature more than 20,000 Kelvin, as you can see in this HR diagram also. So they belong to the spectral types OB type and Wolf-Rayet stars. So Wolf-Rayet stars, these are the evolutionary descendants of massive OB type stars. That is in the later stages of the evolution, these OB stars come to the Wolf-Rayet phases, and they have lifetimes. They live for short lifetimes of the typically for a few million years only. So a very crucial feature of massive stars is their stellar winds. So because as we know that as long as the star is on the hydrostatic equilibrium, that is the outward forces are balanced by the gravity. So but when if there is because of some reason the outward forces they are more, then the matter which is present on the in the stellar surfaces, they come to the interstellar medium. So in case of massive stars, because of the huge radiation pressure, the matter which is present in the outer layers, that is shed into the interstellar medium. So these winds are also called the radiatively driven winds, because the momentum which is in the momentum carried by the photons. Massive stars have huge amount of UV and optical photons. So the momentum carried by these photons, it is transferred to the ions present in the stellar atmosphere, and these winds can lead to, in case of massive star, they lead to mass loss rates of around 10 to the power -7 to -5 solar masses, which is very large as we compare it to the solar wind. For solar wind, the sun loses around 10 to the power -14 solar mass per year. So, and these winds they travel with the terminal velocity of 1,000 to 3,000 kilometer per second, depending upon the different spectral types. And if we see the amount of kinetic energy which is transferred into the interstellar medium because of these stellar winds, it is calculated using this relation. And here I have compared it for the solar wind and the wind from the massive stars. So you can see here that for case of massive stars, around 0.1 times of the volumetric luminosity, which is around 10 raised by 37 to 40 arc per second, it is transferred to the interstellar medium. Although it is only 0.1 times of the volumetric luminosity of the star, still this mechanical energy which is transferred to interstellar medium in the form of stellar winds, it gives rise to multiple observational signatures throughout the electromagnetic spectrum, as I will explain later in my slides. So these winds are very important to study, and overall, if we see these are the main properties of stellar winds are that these are not very homogeneous. Sometimes there are huge chunks of matter which are thrown into the interstellar medium. They have a temperature of around 10 raised by 4 Kelvin, made up of plasma, that is ions and electrons. And the chemical composition of the stellar winds, it depends upon the evolutionary stage at which the star is there. For example, there are 3 kinds of Wolf-Rayet stars: WN type stars, WC type stars, and WO type stars are there. So as these O-type stars evolve to the Wolf-Rayet type phase, the matter which is present inside the core of the star, it comes to the surface. It comes to the surface because of the convection, and when it comes to when it comes in the form of stellar winds, at that time we see spectral signatures from different ions. So in case of WN stars, we see spectral signatures from nitrogen and helium. Mainly it happens because the matter which is present inside the core, which is there because of the hydrogen burning, it comes to the stellar surface, which is rich in nitrogen only through the CNO cycle. And when the stars evolve further, and then helium burning takes place, which makes the carbon and oxygen. And when it comes to the surface, so therefore we see the WC phase and WO phase in the evolutionary sequence. So if we talk about evolutionary sequence, then WN stars comes first, then WC, and then WO type of stars in the evolutionary sequence of OB type stars. So yeah, so these stellar winds, they are important to study because they influence the evolutionary timescales. Because if with that such a huge mass loss rate of 10 raised by -5 to -7 solar mass per year, so they lose us a very significant amount of mass during their lifetime. Sometimes they lose their half of the mass. And the star's evolution, as we know, that it depends upon the mass of the star. So their evolutionary time scale changes, their chemical profiles and their surface abundances also change. As the matter which is present inside the core, it comes to the surface and in the interstellar medium. And they affect their stellar luminosities also. So therefore, next is I want to discuss about the feedback to the interstellar medium because of these stellar winds. So the two important things which I have, one important thing which I have already told is that they impart mechanical energy into the interstellar medium. So this mechanical energy, it can trigger new generation of star formation, as Dr. Neelam has already explained, has given us many examples of triggering star formation from these massive stars. So they can also alter the shape and structure of the interstellar clouds. And sometimes there are also, we see wind-blown bubbles surrounding a massive stars, as shown in this image. So there are bubbles around massive stars, and also they are surrounded by H2 regions because of their huge ionizing radiations. And next thing is that lead to chemical enrichment of the interstellar medium. When the matter which is CNO processed, it comes to the surface, and also the other the heavy nuclide also, which are formed at the WR phase, or in the very heavy mass stars, like up to iron or nickel, they come to the surface in the supernova. And in the supernova explosions, the matter which is formed because of the neutron capture, the nuclides heavier than iron are formed. So massive stars, these are the main input for the nucleosynthesis. Yes. So most of the stars, these massive stars, they are found in the binary or higher multiplicity systems. So conservatively, the lower limit is around 50%, but we expect that there are more than 50% of stars which are found in the higher multiplicity systems. So when two massive stars are bound together by gravity in a binary orbit, and if they both have their own stellar winds, then their stellar winds, they will interact with each other at a place in between these two stars. So at the place of the wind interaction region, because these winds are highly supersonic, so when they interact with each other, there are formation of hydrodynamic shocks in the wind interaction region. So these shocks, where they are formed, it depends upon the momentum balance of these two winds. So the wind interaction region will lie closer to the star with the weaker wind because of the momentum balance. So, and these hydrodynamic shocks, they can give rise to a number of observing features to us. This is also schematic diagram of these are called the colliding wind binaries, where the winds from the two massive stars, they interact with each other. So they can give rise to strong hydrodynamic shocks, and these shocks are appropriate sites for accelerating particle to relativistic speeds. And also in some cases, we have seen that the dust is formed in these colliding wind binaries under very special circumstances, because generally we don't expect dust to form in such hostile environments which are so hot. Formation of dust requires cool temperatures to form, but still we see dust formation in such kind of stars. So because of these phenomena, we see electromagnetic emission of over the entire electromagnetic spectrum from these stars. For example, in the radio domain, we see Bremsstrahlung emission, thermal free emission from both the star winds. They have a temperature of around 10⁴ Kelvin. So in the radio domain, they give thermal free emission, and also because of the relativistic particles, when they are present in the magnetic field, they give non-thermal synchrotron emission in the radio bands, and enhanced infrared emission is there because of the dust formation in few colliding wind binaries. And when these hydrodynamic shocks are formed, so the matter which is present in the post-shock region, that is compressed, and that is compressed, and the temperature also increases and density also increases, and the temperature in the post-shock region, it's around 10⁶ to 7 Kelvin, which lie in the X-ray energy range. So we observe many colliding wind binaries in the X-ray energy range. And when the particles which are there are accelerated in the colliding wind region, they are inverse Comptonized. They inverse Comptonize the optical or UV photon which are in abundance in the case of the massive stars. So they can give rise to the non-thermal very high energy emission, giving rise to gamma ray emission also. And if these accelerated particles, they happen to escape the system, they also give a contribution to the galactic cosmic rays. So so we can say that they are laboratories, like where you can study different type of processes. So today I'm going to show you results which we have obtained for dust formation in a colliding wind binary WR125. So it's an WR125. It's an interesting dust maker. It's a galactic WC plus O9 type star. So this has very special emission properties. Here in this system, the radio emission was seen, which has both the thermal and non-thermal signatures. And also we have seen that the infrared, the mid-infrared flux, the infrared flux increases increased in the during 1990 to 1991. In this system. So it was thought that because of the condensation of dust in this wind closer to the periastron passage, because close to the periastron passage, when the wind density is maximum, there the formation of stronger shocks occur. At that time, the dust formation could be maximum. So the 1991 episode, it was thought to be related to the periastron passage of this system. So this IR axis, it was observed only observed once during 1991, and after that no recurrence we have noticed till now. So to see whether the next dust formation episode in this object will when it will occur, we have observed this source using AstroSat, SXT, and TIRChem-2. in the near infrared band using 3.6 meter Devastal optical telescope. So just for the illustration, I have shown here the WR binary APEC. So it's a triple system. Central one is a WR plus WR system, and another O-type star is also there. So the central system, it has a period of around 100 years. So this is a mid-infrared image. You can see a nice dust plume is there. It occurs because when the central system has a period of around 100 years, and when the two stars move in the binary orbit, and the dust moves in the interstellar medium, so it forms a very nice dust plume here shown in the infrared image. So this is the next is the X-ray light curve of WR125. It is obtained using data from 3 X-ray instruments: Swift XRT, XMM-PN, and AStroSat S60. So in this light curve, you can see that during 2017, in AStroSat, I have shown here, first of all, the upper limits of the counted because the source was not detected. Source counted was only 1.5 times larger than the background counted. So we have shown it's counted as an upper limit only. So during June 2020, we have seen the X-ray counted has decreased. It has reached its minimum during the entire light curve we have here. And also when we perform the X-ray spectroscopy of WR125 using the 2-temperature thermal plasma model, so we have obtained flux in the broad, soft, and hard energy bands in all 3 energy bands using the entire data from 1980 to 2021, which was available till now. So again, here you can see that during 2020 the flux has decreased to the minimum level, and similar flux values were also noticed during 1990 episode also. So it may show an orbital period of like 29 years for WR125 for when the X-ray flux has reached its minimum. So to confirm it further, we have performed NIR monitoring of WR125 in the JHK bands with TIRChem-2. So this light curve here shows the K-band magnitude of WR125 by taking data from literature and our observations also. So again, here you can see here that during the recent observations which were made in 2017 to 2021, close to 2021 and 2020, the infrared flux is larger, it is close to those levels which we observed in the previous dust formation episode. And also again, the infrared light curve also shows a period of around 29 years only. So this dust formation episode, we could, after monitoring in the X-ray flux and the infrared wavelengths, we could say that the dust formation again, it has begun in case of WR125 after 29 years. So this is important to study such kind of indirect processes occurring in the colliding wind binaries to infer the multiplicity of these objects, which is otherwise very difficult in case of, especially in case of long period systems. So for example, this is a system with 29 years. So if we try to find its orbit or orbital period using different other methods like radial velocities, etc., so they will demand a huge time and continuous observations also. So but if these kinds of methods like observing X-ray emission, IR emission, and studying the non-thermal emission from the colliding wind binaries, they gives us indirect ways to study the multiplicity of these stars. So yeah, that's it about the scientific part I wanted to talk today. So, and at last I want to share something here today, that these are the for this Women's Day, that they are the everyday inspirations for us, I have seen here personally from the last few years, and they are doing so well in all aspects of their life, like personal and professional also. So they are the best examples to show that women can do anything in every area of life. Thank you so much.
Thank you, Bharti. Questions?
Bharti, I have a question. Hello, Bharti.
Yes, sir.
Yeah, you said the mass loss in WR or W N or WC phase of this WR star is 10⁻⁻5 to 10⁻⁻7, right?
Yes, sir.
This mass loss is consistent over this outburst phase, or I mean, this is a time evolution of this mass over that evolution phase.
No, sir, this is not like, for example, in some cases when there are some giant eruptions from the stars, at that time the mass loss is very huge, and after that again it comes to the
it comes back to its normal level. Yeah.
Yes. It's not. We cannot say that it's consistent over the entire lifetime of the star.
So this mass loss, because this is a huge mass loss, 10 to the power minus 5 to 10 to the power minus 7, and for a massive star, even they are in the main sequence phase, because what mass loss we are talking about, that is the post-main sequence phase, right? WR phase, right?
So there are some WR stars even on the main sequence also, which are very high mass stars.
Yeah, because for a normal main sequence high mass star of that order, I mean 10 solar mass or even more, so we always have a high mass loss, whether it is not a a WR star, right? So in massive star, mass loss rate is quite high due to the radiation.
Yes, sir, because of radiation. Yeah, sir.
So when it goes in this WR phase, so in a particular phase, we have this 10 to the power minus 5 to the power minus 7 solar mass, and it is, you said it is not a consistent, right?
Yes, sir. Yes.
It changes. Maybe at some stage it's quite high, but at the later phase, it is not that much high.
Yes, like for example, for the case of O-type star, we can say that it's around 10 raised, it's slightly lower as compared to the WR phase, because at that time the winds are more, the star is losing mass at a very large rate because of the very huge radiation pressure.
Yeah.
And these are more active as compared to the O-type star. Also, there are some depending upon the mass, it happens actually.
Yes, of course, it depends on masses.
Yes, sir.
Other thing is that in WC and WN star, you will not have any hydrogen burning cell, right, at any place, because
in WN stars, it's possible to observe some WN stars in the hydrogen burning phase also, but in the case of WC, it's purely helium burning.
But as I understand, when you say the WN, so its outer cell is nitrogen, right? So because the outer, its temperature is so huge that yes, all these hydrogen and heliums are already gone. So that's why this, I mean, whether it's WC or a WN, this carbon and nitrogen has reached to its cell level, right? This hydrogen, carbon.
So actually, the nitrogen which was there in the core, because of the hydrogen burning through the CNO cycle, it comes to the surface, and when it is shed to the interstellar medium in the form of winds, so we see the nitrogen features in the spectrum.
But it is that nitrogen which is burning at the core, or it is that nitrogen which is at the cell and it is burning because of the high temperature?
No, so it's core. When the core material it comes to the surface, at that time we see the features because of the WR stars.
So you are saying that whether it is WC or WN, these C cell or N cell are not periphery, and these carbon and nitrogen are coming from the core, which are in the photosphere, and we are seeing that.
Yes, because a very large amount of mass is lost. Sometimes half of the star's mass is lost because of these strong stellar winds.
But when you have such a high mass star and your core temperature is quite high, this core burning in various cells will not move towards outer region. Like what happens, when we have the hydrogen cell initially, then hydrogen cell move to outer world. We have the helium cell and then carbon cell, nitrogen cell, and all up to the iron cell we have. And all these cells, various cells, whether it's hydrogen, helium, it can move. It keep on moving outwards, right?
Yes, sir. Yes, sir. Yeah.
So at some stage, your temperature is so high, even helium cell you will see at the your periphery, your outer cell with the helium cell. And if you increase even temperature, and at some stage, even that helium is gone, and now it is in the carbon form.
So I think that in the case of WR stars, it comes mostly from the emission is mostly because of the matter which comes from the core to the surface.
Okay, fine. For this discuss this.
Okay,
fine.
Any other question? Can I ask one?
Yeah.
It's a much more general question. So you were talking about very massive stars and the stellar winds and stellar activity from such kind of stars. But even the smaller stars, say sun-like stars, when they are very young, I mean,
Yeah.
the main sequence phase has just started. At that time, they are much more active.
Yes.
Like a lot more stellar winds.
I guess
And
at that time also they lose mass from
yes,
the
yes.
pre-main sequence stars also.
Yeah. So such kind of features do you see with such small young stars as well?
Certainly they will show the emission line features also in their spectrum, but I'm not sure about how much mass they lose in their in that time, that what is the mass loss rate. But these type of features, I think we can see in those cases also.
Okay. And what about the dust formation mechanism that you were?
It is proposed that during the when the first of all, in case of WR stars, dust formation we till now we have observed only in the case of binaries. So, in the case of binaries, when as I have told that when there are formation of hydrodynamic shocks, at that time the density in the post-shock region increases. So those enhanced density, they can give rise to dust formation when there are certain circumstances are met in those regions, like temperature of around 1000 Kelvin. But how such low temperature is attained there, that is still debatable. So that is topic of research, and this formation is seen only in the case of WC stars, only not WN or WO stars, because of the presence of carbon in these type of stars.
Thank you. Okay, so if there are no more questions, we'll stop here. So thank you, Bharti. And I would also like to thank all other speakers for accepting to give the talks at such a short notice. So with this, we come to the end of the first day's activity. Tomorrow, we are going to have a panel discussion on obstacles, achievements, and challenges by women in STEM fields. And the panel will be led by Dr. Priya Hassan from Maulana Azad National Urdu University. The panel discussion will happen in online mode, and again it will start at 11 a.m. and I'll be sending the Zoom link for that as well. And with this, we come to the end of the first day's activity. I thank all of you and even the audience for joining us. Sorry again for the delay in sharing the Zoom link because of some issue with the email server. Okay, thanks. Thank you, everyone. Javed, you can end the stream.